Now we're going to look at this process of gathering a subset of a population. The idea is when you have a population, we want a subset of that population that's representative, and we call that a sample. So let's look at this data set. It's a census of Turin, Italy. So in 1705, the French, they were attacking Turin, Italy. And in part to recruit men for war, the officials in Turin, Italy, they surveyed all the inhabitants of the city. And they recorded information on people's names, their age, their gender, where they were born, as well as the weapons they had. And the idea is that they wanted to conduct this census so that they could recruit men for war. Now, let's ask a question. What's the average age of people living in Turin, Italy in 1705? Well, this is data from the 1705 census. And so we can see each of these rows, they're residents of Turin, Italy. These are the cases. And then the characteristics, they're different variables. And so you can see we have the last and first name of each person. We have the person's age and their gender. But this is a population. Those are all population parameters because it's based on a census. So since we have all the people in Turin, Italy, we can just calculate the population mean for age. We can calculate the true population parameter for mean age. And we find, based on this data set of the population, the average age is about 30.14 years in the population in Turin, Italy. But of course, if you recall, when we talk about inferential statistics, the idea is to collect a representative sample to say something about the population. So conducting a census is very expensive and difficult. Back in 1705, they didn't know about inferential statistics, so they just collected data on everybody. But they could have saved a lot of time and money if they just collected a subset of that population through a sampling procedure. So let's collect a simple random sample. So here's a sampling frame. This list is truncated, but it's more or less the number of people in the population. So suppose we didn't actually collect the census, and all we have is a list of everybody. This is our sampling frame. Right? The idea is that when we collect a random sample, we're just going to randomly select these rows of this sampling frame. And for this exercise or this example, we're going to sample people. We're going to use replacement. Okay. So let's take a sample. All right, we're going to take a sample size of 10 people from our population, and we're going to measure the same characteristics as we actually did for our census. So we're going to look at age, gender, birthplace, and so on. The entire point is we're going to see if we can use this sample to guess the mean age of people living in Turin, Italy. Because if you recall, normally we wouldn't have the actual population. We just have that sampling frame. So here's a random sample that we've collected from that sampling frame. So this is a sample size of 10 people. And our goal is to see, well, we're trying to guess the average age in the population. So just based on this sample, this random sample, you can see, well, our best guess for that population mean is our sample mean. And we get a sample mean of 22.9 years. So if we just use this random sample, we'd say, well, I think the average age in Turin, Italy in 1705 is 22.9 years, which we know is off because we have the population. But this point estimate, this sample mean, it's really our best guess for that population mean, right? Because of course, we wouldn't actually have conducted a census, so we wouldn't really know what the population mean is. Now we might ask, how far off are we, right? Well, sample mean is 22.9, the population mean is 30.14, so we're kind of off. But let's see what happens if we take another sample of size 10 and we calculate X bar again, the sample mean again. So this is a different random sample from that sampling frame of all people living in Turin, Italy in 1705. And now our sample mean for this different sample is 30.6 years. Right? So it's a little bit above the population mean, and it's much greater than our previous sample mean. But let's say what happens if we collect yet another sample. So this is a different random sample. And again, we're going to look at the average age in our sample. And now we get a sample mean of 33.1 years. Right? This variation between these sample means, we call that sampling variability, because our point estimates, our best guesses for the population mean for each sample, they jump around, they bounce around, right? So we call that sampling variability. But for now, let's use some subscripts to keep track of these point estimates. So far we have the sample mean for the first sample, which is 22.9, the sample mean for the second sample, which is 30.6, and the sample mean for the third sample, which is 33.1. Right? These sample means, they're bouncing around. There's variation, there are differences between these sample means. And that variation is just a reflection of the fact that when you collect a random sample, right, those sample means, they're going to change, they're going to jump around, right, just through sampling variability. Well, we know the population mean is 30.14 because we have the census data, right? And you can see sometimes the sample mean is above the population mean, and other times it's below the population mean. But if you notice, okay, if you take the average of these three sample means, right, the average of 22.9, 30.6, and 33.1, right, you take those three sample means and divide by 3, you get 28.67 years, which is pretty close, okay, to that population mean of 30.14. So let's create a dot plot of our sample means that we've collected, just to keep track of what's going on. This is a dot plot. You can see we have 3 sample means, right? But this looks kind of ridiculous, okay? So why don't we collect 10 sample means, each based on a sample size of 10 people, and why don't we see what happens when we collect a dot plot of that, when we see the distribution of sample means, okay? This is what our distribution looks like. This is a distribution of 10 different sample means from Turin, Italy, right? And when you take the average of these sample means, that average is 32.5, okay, which is pretty close, okay? You can see that some sample means are above, so we have some sample means that are almost near 40, some sample means are really down to 25, but on average, these sample means are pretty close, about 32.5 years, to that population mean, which we know of 30.14. Well, what happens if we collect 30 samples, right? Each dot here is a different sample mean when we have 30 sample means in total. Now the average of these sample means is 30.08. We're getting a little bit closer. The more samples we collect, right, the more sample means that we calculate and put in a distribution, the average of those sample means is now a little bit closer to that population mean. Well, what happens when we collect 100 samples, and each time we collect a sample, we calculate a sample mean? Well, now that average of those sample means, the average of this distribution of sample means, is now 30.8. We're getting we're still a little bit off, but we're fairly close still to that population mean of 30.14. Well, what happens if we collect 1,000 samples and calculate a sample mean for each one of those samples and create a little distribution of those 1,000 sample means, and then we calculate the average of those sample means? When we calculate the average of the sample means, we get 30.12. You can see we're converging on that population mean, right? Even though it's just a distribution of sample means, we're converging. So here's an example in which, suppose we collected 100,000 sample means, right? And we create a distribution. Now, you only can collect 100,000 sample means from a population of the size of Turin, Italy in 1705 if you sample with replacement. That's why we use with replacement. But the idea is that this distribution of sample means, the average of this distribution is very, very close to the population mean, right? And you can see that some sample means are above, some sample means are below. But most of those sample means, in fact, the most likely sample mean is right on that population mean, right? This is what we call a sampling distribution, okay? When we have a distribution of sample means of the same sample size n, lowercase n, from the same population, this distribution of sample means we call a sampling distribution. That variation in that sampling distribution reflects sampling variability, the fact that samples are going to differ from one another just through the process of a simple random sampling procedure. Importantly, this sampling distribution, this distribution of sample means, it's centered on that population mean mu, right? And although the mean from any particular sample is going to be off. It's going to be above or below. On average, the sample mean is our best guess for that population mean. Right? You might ask, how far off is our guess? Right? Our point estimate, our guess for that population mean is going to be our particular sample mean that we've gathered. Well, the standard deviation of the sampling distribution, we call that the standard error of the sample mean. This is given by this formula. It's a standard error. It equals the population standard deviation divided by the square root of our sample size. If you note, the larger the sample size, right, then a smaller standard error of the sample mean will occur. Okay? And then there will be a smaller spread of the sampling distribution. Because the standard error of the sampling mean, it depends on two values. It depends on the population standard deviation, which you actually can't control based on the sample size. It's just a fact of nature. But the smaller that population standard deviation, the smaller the standard error of the sample mean, the smaller that standard deviation of the sampling distribution. But what we do have control over is the sample size. Right? For a given population standard deviation, the larger that sample size, the smaller the standard deviation of the sampling distribution. Or to put it another way, the smaller the standard error of the sample mean. We call it the standard error because you can think of the standard deviation of the sampling distribution as an error. Okay? It's how far off we expect to be on average in terms of a sample mean and the population mean. Okay? The standard error of the sample mean, the important point about it is that we can actually calculate it in our instance because we know the population standard deviation for our variable. Our variable is age, so we go back to the census data, and that population standard deviation is 17.86 years. Right? So suppose we collect a sample size of 10, as we've been doing, then we know the standard error for any one of our sample means is going to be that population standard deviation divided by the square root of a sample size. So since we know the population standard deviation, we can divide 17.86 by the square root of our sample size 10, and we get this value of 5.65. That is the standard deviation of the sampling distribution. That's how far off in years we expect to be across our different sample means. Right? So let's look at this distribution of sample means with using 100,000 samples. Each point here, the points are so small you can't even see them, they're different sample means. And you can see that this distribution of sample means, or sampling distribution, it's centered on the population mean mu. It's very close to 30.14. And then the standard deviation of the sampling distribution, the spread, how far off are any particular, on average, we expect the sample means to be from the population mean, that standard deviation, right, is given by 17.86 divided by the square root of 10. Right? Now, the important point is what would happen if we created a sampling distribution, a distribution of sample means, based on a sample size of 100 rather than 10. Well, here we have two examples. We have a sampling distribution. Okay, these are 1,000 sample means, each one based on a sample size of 10. So we collect 10 random people from the population, okay, calculate their average age, right, throw them back in the population. And we repeat that process repeatedly. Well, on the left-hand side, each of those samples is based on a sample size of 10. Right? For the other graph, we have 1,000 samples based on a sample size of 100. Right? And you can see the spread, right, the standard deviation of the sampling distribution, how far off we expect the sample means to be, it's less the larger the sample size. Okay, that should make sense because the standard error is just that population standard deviation divided by the square root of n. The larger that sample size, the smaller the spread. In the same way, you have to keep in mind the population standard deviation is fixed. So, 1 over 10 versus 1 over 100. Right? The larger that fraction, right, the larger the denominator of that fraction, the smaller that standard error, the smaller that standard deviation. So when we have a sampling distribution centered around the population mean, right, the smaller that spread, the tighter that distribution is around the population mean, okay, we're not going to have as much sampling variability. Right? We'd expect our sample means typically to be pretty close to that population mean. If that sampling distribution is really spread out, if that standard error is really quite large, then we're going to see a lot of variability in our sample means. Right? We might be concerned that any particular sample really might be far off. Okay, so in general, you want a pretty large sample size, because a larger sample size, it gives us more information, and we expect that sampling distribution, that distribution of sample means, to be bound more tightly around that population mean. So the other point is that notice the shape of the sampling distributions, right? It's not only centered on the population mean, it not only has a standard deviation given by the standard error, which is the population standard deviation divided by the square root of n, where n is our sample size, but it's also mound-shaped, right? There's kind of this peak in the middle, centered on the population mean, and it's symmetric, all right? So the left and right sides of the distribution look more or less the same. This shape of the sampling distribution and this process of repeatedly randomly collecting samples and plotting these summary statistics, these sample means, it's so important we will cover it again and again. It's really the foundation of inferential statistics. There are a couple things to know about our discussion of sampling procedures and the sampling distribution. Some of the commonly used sampling methods include simple random sampling, stratified sampling, and cluster sampling, and we looked at both one-stage and multi-stage cluster sampling techniques. A point estimate is simply our single best guess without additional information of a population parameter. So when we collect a sample average from a simple random sample, that's our single best guess for the population mean. Then we also covered the sampling distribution. The sampling distribution is roughly mound-shaped and symmetric, and it's centered on the population mean mu and has a standard deviation given by sigma, the population standard deviation, divided by the square root of our sample size. And with that, we will conclude our discussion of sampling procedures and the sampling distribution.